Hello again. This is Math 2232 coming to you from the College of DuPage. And the title of this lecture is Partial Fractions. And this is, even though it sounds a little bit like it, this is not integration by parts. This is a different technique called partial fractions. Please be an attentive learner while watching this video. By way of introduction, let's start with an integral we know how to do. This is the ratio of polynomials, and we know how to do this one. So the indefinite integral of 2x minus 1 over x squared minus x minus 6 dx. Since the derivative of the denominator is 2x minus 1, we see that du, the numerator, is exactly the derivative of the denominator. So we can use the substitution u equals x squared minus x minus 6, 1 over u, and then we back substitute because this is an indefinite integral. You get the natural logarithm of the absolute value of x squared minus x minus 6 plus c. So if the numerator is the derivative of the denominator, or if it's a constant multiple of the derivative of the denominator, it's pretty easy to do this, and we knew how to do this before. However, often the numerator isn't the derivative of the denominator or a constant multiple thereof. For example, consider this problem, which is going to be our first example. So this is the integral, the indefinite integral of 3x plus 11 over x squared minus x minus 6. And the numerator is definitely not the derivative of the denominator nor a constant multiple of that. Therefore, simple substitution that we used up here won't work. However, if we notice that the integrand can be broken up as follows, you see this ratio is actually the same as this. 4 over x minus 3 minus 1 over x plus 2. And you might notice that x minus 3 times x plus 2 is the factorization of this denominator. Maybe you're remembering it, maybe you're not. But anyway, this is the technique. So we do this decomposition, rewriting this integrand this way, and then we do the sum of the integrals, and it is very easy to do. This is called partial fraction decomposition, and many integrals involving rational expressions can be done if we first do partial fractions on the integrand. This is extremely significant when you're doing Laplace transforms in differential equations, so it is a very important technique. So let's do a quick review of partial fractions. We'll start with the rational expression of the form f of x is equal to p of x over q of x, where both p of x and q of x are polynomials, and the degree of p of x is smaller than the degree of q of x. Now, if the degree of the polynomial, that's the largest exponent in the polynomial, if it is top heavy, what you're going to do is long division, dividing q of x into p of x until you get it in this form where the degree of p of x is strictly smaller than the degree of q of x. This is important to remember. The partial fractions can only be done if the degree of the numerator is strictly less than the degree of the denominator. And once we've determined the partial fractions can be done, we factor the denominator as completely as possible. So step one is making sure the degrees are correct, and then you factor the denominator as completely as possible. So factoring is a skill. Then for each factor in the denominator, we can use the following table, which you should commit to memory, to determine the terms that we pick up in the partial fraction decomposition. Students have told me this is a very simple table, and I think it is very useful. For each factor in the denominator of the form ax plus b, you get a term in the partial fraction decomposition that is capital A over ax plus b. Now the capital A, the lowercase a, and b are all constants. And later on I'm going to talk about the Heaviside cover-up technique, and this one is Heavisidable. And many of my engineering students love problems that can be done with the Heaviside cover-up technique. Each factor in the denominator of the form parentheses ax plus b whole to the k power, where k is an integer, generates the following terms in the partial fraction decomposition. It is a1 over ax plus b plus a2 over ax plus b whole squared plus dot 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 plus ak over a x plus b whole to the k power. And again, although this is not completely solvable by the Heaviside cover-up technique, this is going to be partially Heavisidable, so that is a good thing. Now, some terms will be irreducible over the real numbers. That means they have complex roots. So we end up with a factor in the denominator that looks like this: ax squared plus bx plus c, that cannot be factored. Now, each factor in the denominator that is like this generates a term in the partial fraction decomposition that looks like capital AX plus B all over AX squared plus BX plus C. And it's also possible to get one of these raised to a multiplicity k. So if you get ax squared plus bx plus c whole to the k power, it generates several terms: a1x plus b1 over ax squared plus bx plus c plus a2x plus b2 all over ax squared plus bx plus c whole squared plus dot dot dot, plus finally akx plus bk all over ax squared plus bx plus c whole to the k. Now you should notice that the first and the third are really special cases of the second and the fourth. And there are several methods for determining the coefficients for each term, all the capital A's, and we'll go over some of those in our examples. And I will discuss both within here and separately the Heaviside cover-up technique. Okay, so example 1 is evaluate the following integral. This is the one that we actually already did, so I'm not going to ask you to do this. I'm going to go straight to the solution. But we are going to do partial fractions here. So you see, first thing we do is we observe that the numerators of degree 1, the denominators of degree 2. So that means I don't have to do long division. Then I factor x squared minus x minus 6 to get this. And then from my table I know that this expression is the same as a over x minus 3 plus b over x minus 2, because they were distinct factors. Now what I'm going to do is I can get a common denominator over here, and the common denominator is going to be x minus 3 times x plus 2. So I get that this is going to be, here I multiply top and bottom by x plus 2, here I multiply top and bottom by x minus 3. So I get that this is a times x plus 2 plus b times x minus 3 over that. And then I simplify, and the numerators have to line up exactly. So that means that 3x plus 11 has to be the same as a times x plus 2 plus b times x minus 3. Now I simplify this and I see, well, the coefficient on the x here is a 3, and the coefficient of the x on this side is a plus b. So we conclude that a plus b has to be 3. And then I have an 11 that's a constant. So 2a minus 3b must be 11. Notice that this is 2 equations and 2 unknowns. You know how to solve that, and you would have to solve that. And so a is equal to 4, or b is equal to minus 1. So that is one way to approach this, and then we do the integral. Another way, though, is the Heaviside technique, and there I can say what happens when x equal minus 2, and that tells me b has to be minus 1, and what happens when x is equal to 3, and that says that a is equal to 4. So again, I solve this, and I know what those coefficients are, and this is using the Heaviside technique that we will talk about separately. Again, my engineers really like this technique. So now what we've done is we know what a and b are, so we can write it this way, and this is the same answer we got earlier. And so this is the answer to the problem. Now, before moving on to the next example, I should make a couple of notes. So many of the integrals and partial fractions come down to the type of integral seen above. They're going to be natural logarithm kind of things, and you can do those. But another one that comes up often is this one. It is 1 over x squared plus a squared dx. This comes up a lot. You'll see it in the problem. And the antiderivative of this is 1 over a. the inverse tangent of x over a plus c. Perhaps you remember this from Calc 1 at COD. If not, just memorize it now. And you can prove that this is true by taking the derivative of this side and showing you get the integrand. But keep this in mind. Here's a problem for you to do. Evaluate the following integral. This is x squared plus 4 over 3x cubed plus 4x squared minus 4x dx. You know what to do. Let's see how you did. Okay, let's begin by realizing that I have a cube in the denominator and a squared in the numerator, so I don't have to do long division. And then I start looking and I say, oh, I have 3 linear factors when I factor this completely. So this is x plus 2, and this is 3x minus 2. So that is a over x, b over x plus 2, and this is c over 3x minus 2. This is from my table. Now, one way that you can do it is by getting a common denominator here and aligning the coefficients. And if you were to do that, then you would be concluding the numerator, this is x plus 4, is equal to, and this is going to be a times that, plus bx times this, plus cx times that. And if you equate coefficients for x squared, x, and the constant, you'll get this system of 3 equations and 3 unknowns. So you would solve these to find out what a, b, and c are. Or you can set x equals 0, x equal minus 2, and x equal 2/3. This is the heavy side technique, and conclude that a is minus 1, b is 1/2, and c is 5 over 2. By the way, you'll get the same answer if you solve those 3 equations and 3 unknowns yourself, but you're going to be doing that by hand. So keep that in mind. Note that unlike the first example, we have coefficients that are fractions. That happens, and that's fine. So the integral then, this is equal to, I write like this, I do the sum of the integrals, and I get this. Now, notice that when you're integrating this third one, you had to do another u substitution, and so the coefficient here actually is 5 over 6. So make sure you follow how to do this, but there's the answer for example 2. Example 3, evaluate the following integral. This is the indefinite integral of x squared minus 29x plus 5 all over x minus 4 whole squared, and this is x squared plus 3. And by the way, I could do definite integrals, you just would plug in the values, but this is the one that we're doing. You know what to do. Let's see how you did. Again, the denominator is of degree 4, the numerator is of degree 2. We don't have to do long division, but we do have to, and I was being nice to you here that I factored this for you, so I have the factorization. But now, by Heaviside, what happens is we end up getting a different decomposition. We have a over x minus 4 plus b over x minus 4 whole squared because this factor was squared. And then here I have cx plus d over x squared plus 3. Now, you get common denominators, multiply top and bottom. There's quite a bit of an algebra involved. I encourage you to do the algebra, and this is what you get when you do the calculation. And then you expand it. And notice what happens now. The coefficient here of x squared is 1, and the coefficient of x squared here is all of this. So this is equal to 1. The coefficient of x cubed is 0, so a plus c has to equal 0. So those are the first 2 equations. The coefficient of x1, when you simplify it, was this, and that is minus 29. And the coefficient of x0, which is the constant, was all these, and so that has to equal 5. So that is 4 equations in, 4 unknowns. You have to be able to solve this. And so what you get is a is 1, b is minus 5, c is minus 1, and d is minus 2. So that means this is the integral. I do the sum of the integrals. And notice that now this last one, I actually break this into two integrals. The first one is minus x over x squared plus 3, but then it is 2 over x squared plus 3. This last integral is of the form a constant over x squared plus a squared. This will give rise to the inverse tangent, and so I get this term, which is a logarithm term, this term, which is just a normal integration term, substitution. This is a logarithm term, but this is the inverse tangent term. Make sure you see where all of this comes from. Example 4. Evaluate the following integral. This is the indefinite integral. This is x cubed plus 10x squared plus 3x plus 36 over x minus 1. And then this is x squared plus 4 whole squared. You know what to do. Let's see how you did. Again, the degree of the numerator is 3. The degree of the denominator is 5. After you multiply that all out, so we don't have to do long division. But then I start looking at the factors. So I realize I get a over x minus 1. But then I have x squared plus 4 whole squared. So I get two terms. The first looks like this, and the second looks like this. You see how you have to memorize that table. It's not really that bad, but you do have to memorize it. So now I have A, B, C, D, and E, 5 constants to determine. So what I'm going to do is get a common denominator here, do algebra, and I'm going to equate the coefficients. And so this is equal to this when I completely simplify it. So A plus B is the coefficient on x to the fourth, so that is 0. C minus B is the coefficient on x cubed, so that is going to be x cubed is 1. And then this is the coefficient of x squared, and x squared is 10, so that coefficient is equal to 10. X has a coefficient here of this, and that's equal to 3. And last, the constant is 36. So I equate the coefficients. I have 5 equations, 5 unknowns. We have to solve that. But A is 2, B is minus 2, C is minus 1, D is 1, and E is 1. And the fact that that's 0 actually is a little bit of a blessing. So we get this. Here we do it term by term, so that is minus 2 over x plus 4, minus 1 over x plus 4. So you see we are going to get an inverse tangent here, and here I get a u substitution that I can do. Make sure you follow all these steps, but this is your final answer. Now, to this point, we've only looked at rational expressions where the degree of the numerator was strictly less than the degree of the denominator. Of course, not all rational fractions will fit into this form. In particular, I ask questions sometimes on exams that require you to do long division. And so here's an example where we have that. Here, the degree of the numerator is the fourth, and the degree of the denominator is cubed. So we've got the definite integral of x to the fourth minus 5x cubed plus 6x squared minus 18 all over x cubed minus 3x squared dx. You know what to do. Let's see how you did. Okay, first we do long division, and so x cubed goes into x to the fourth x time. I multiply it all the way around, and I get this, and I subtract. When I take minus 5 here, they cancel out by design. Here it is minus 5x cubed, and this is minus and minus, so that's plus. So I get a net of minus 2x cubed, and I bring down the remainder. Now this goes into this minus 2 times. I multiply around and get this, and then I subtract. So these cancel out by design. This will also cancel out by design, and I'll get minus 18. So when we finish the long division, we get that this is x minus 2 minus 18 over x cubed minus 3x squared. Now this is the only one we're doing partial fractions on, but let's do partial fractions on that one, and we have to factor it. So that is x squared times x minus 3. So we can look at this as a over x plus b over x squared plus c over x minus 3. And we can get common denominators, and we set this up. We can get a bunch of equations, but either way, we get the equations, or we use actually, you can only use a little bit of Heaviside on this, but anyway, you can find that b is equal to -6, c is 2, and a is -2. So the whole integral, though, is I have to integrate the x minus 2. It's still there, and then minus, and this is what I changed the remainder into. So I'm going to integrate this to get 1/2 x squared minus 2x, and I integrate each of these terms. And that is the answer to this example 5. Now, in the previous example, there were actually two different ways to deal with the x squared. One was to treat it this way, and the other was to treat it this way. Now, you get the same answer. And so you might say, well, why are we talking about this? Well, the answer is simple. If it will work for x squared, but it'll also work for x cubed or x to the fourth. So if you're doing x cubed, in the denominator, you could say, oh, it's a over x, b over x squared, c over x cubed. And x to the fourth could be this way. Here's another example. Evaluate this integral. So this is the indefinite integral. This is x squared over x squared minus 1 dx. You know what to do. Let's see how you did. Now, we have the same degree, so we have to use long division. I'm not going to do the long division, but if you divide x squared minus 1 into x squared, you get 1 plus, I think I actually have asked this problem on test before, but x squared minus 1 divided into x squared, you get 1 plus, and this is 1 over x squared minus 1. So the only thing you're going to do partial fractions is on this. Now that factors into x minus 1 times x plus 1, and you can use Heaviside on this, and you will conclude that this is b is minus 1/2 and a is 1/2. So that says this integral is this part of it, and notice that we're integrating the 1, and that's going to give us the x, and this is the rest of our answers. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. We're all on this together. God bless you all.